Yeah, thanks a lot for having me. My name is Tim. We recently did a study on the changes in the drivers of compound flooding in Europe. We tried to project those changes using CMIP6 simulations, and that's what I will talk about today. So for those of you who don't know, compound flooding is really about the co-occurrence of different drivers of flooding. So for instance, when heavy rainfall and storm surge happen on the same day or in close succession, the severity of the resulting flooding may be higher than if those drivers of flooding would happen in isolation. So an important question then is, what is the probability that these drivers co-occur? There have been quite a few studies looking at these joint probabilities for historical periods. So what you see here is an example for the UK by Hendry et al., who looked at the joint probability of storm surge and river discharge extremes. And really, you clearly see that there's a spatial pattern to those joint probabilities. So in the case of the United Kingdom, the joint probabilities of storm surge and river discharge extremes are higher on the west coast than on the east coast. And this has to do with the prevailing direction that storm systems travel over Europe. So while there have been quite some studies looking at historical joint probabilities, we know quite little about how these joint probabilities may change in the future. And that is because the existing studies, which are very few, are only based on very small ensembles of climate model simulations. So for Europe, in fact, there are two studies who looked at 5 or 6 climate model simulations. And their projections were, in addition, also only based on one high emission scenario, so RCP 8.5. And well, of course, you can imagine that introduces uncertainties. So for instance, because climate models differ from each other, but perhaps even more importantly for this situation is internal climate variability, because we're dealing with very extreme events, and therefore internal climate variability can have a large influence on your projections. And finally, of course, we want to know what's going on for other emission scenarios as well. The reason that these studies are based on such small climate model ensembles is that storm surges are not an output of the global climate models in CMIP. So global climate models simulate wind and pressure and changes in wind and pressure, but not storm surges. So we need something to translate those changes to changes in storm surges. And typically that's being done with hydrodynamic models, which need to be global and high resolution, ideally, and are therefore computationally expensive. And this has limited the size of model ensembles in previous studies. So what did we do to address those limitations? We looked specifically at the joint probability of storm surge and precipitation extremes using a much larger ensemble of CMIP6 climate model simulations than previous studies. So here you see an overview of which data we used. We gathered data from 27 different CMIP6 models for not just the high emission scenario, but also medium emission scenario. And for all the different models, we used all the initial condition simulations available. So those are simulations for the same greenhouse gas concentration changes, but they start at a slightly different moment in time. So if you average all those simulations, you can partially filter out some of the internal climate variability. And then you're left with a better idea of the force changes. So I just said that deriving changes in storm surges from those simulations is computationally expensive. So how did we do that? Well, that's why we decided to use a data-driven storm surge model instead of a hydrodynamic model based on work by Mike Tedeschi et al. And another interesting fact of our methods is that we used a data proximate analysis in the cloud. So we analyzed CMIP6 data stored on Google Cloud. We looked at the daily CMIP6 data, so that's quite a large volume of data for that many simulations. And the advantage of doing this analysis on the cloud is that you don't have to get all that data to your local environment. Instead, you can bring your analysis to the cloud. Things are much faster and also much more reproducible. So this is done in collaboration with Leap at Columbia University and the Pangeo platform. A few more words about how the data-driven storm surge model works. So we are applying this storm surge model to about 124 tide gauges over Europe. And the model is trained on observations, even though it's applied to climate model simulations. So what we used for that model training is atmospheric reanalysis era 5. And we took two variables from it, sea level pressure and the wind speed. And we took that data at a few grid cells around each tide gauge. So you see an example of that here for a tide gauge in the northwest of France. And from that data, which is a function of time, we extracted the most important patterns explaining the data, so using empirical orthogonal function analysis. On the other hand, we have observations at those tide gauges. And from those observations, we subtracted predicted tides. So that leaves us with non-tidal residuals. And we want to predict the daily maximum of those non-tidal residuals. So simply with that input and output data, we can do a multilinear regression where the empirical orthogonal functions are the x's in the equation and the storm surge predictance is the y in the equation. And doing that gives us regression coefficients that we can then apply to the CMIP simulations. And I don't have the time to show you how well this works, but of course we tested that. And we focused here on the timing of the storm surges. So that's most important for evaluating joint probabilities. And especially with that aim, this model worked quite well. So what happens if you apply that statistical storm surge model to CMIP6 simulations and then look at the joint probability of things? In this figure, you see the number of joint storm surge and precipitation extremes per decade, which is a relatively simple metric of joint probability. And on the left panel, you see the historical probability based on observations. So again, the atmospheric reanalysis combined with tide gauge data. On the right-hand side, you see what happens when you do this for CMIP6 simulations. So using that statistically estimated storm surge and precipitation from CMIP6 simulations, and then taking the average of all the initial condition members and also of the model. So this is the ensemble mean. Well, you can see by comparing these two figures that the spatial pattern between those actually agrees quite well. Again, those higher joint probabilities on the western coast in Europe, which have to do with the direction of storm systems, and is also known from previous work. But we can also now look at feature changes using the CMIP6 data. And we did that again for the two emission scenarios, the medium and the high one. And for both of them, we noticed that increases in the joint probability are projected for the northwest of Europe. And in much of the southwest of Europe, actually decreases in that number are projected. So the spatial patterns between those emission scenarios are very similar, and perhaps unsurprisingly, the absolute magnitude of the changes is larger the larger your emission scenario is. We can also say a bit more about what causes these changes in joint probability. So here you see again those total changes for the high emission scenario, and you can decompose those, for instance, into changes driven only by changes in precipitation extremes, which lead to increases in the joint probability over the north of Europe and decreases over the Mediterranean. And this has to do with a combination of thermodynamic and dynamic changes in the atmosphere, which have also been reported in previous work. And similarly, you can do that for the storm surge driven component, which is mostly negative over Europe. If you combine the two, you get pretty close to the total changes, but not entirely. So the remaining difference is caused by changes in the dependent structure between precipitation and storm surge extremes. And as we explain in the paper of the study, that is at least partially explained by shifts in the season in which those extremes are projected to occur. Since we use a much larger ensemble of climate model simulations than before, it's natural to ask what the sensitivity of the projections are to ensemble size. So for this, we wondered how large does your ensemble need to be so that at least the sign of the ensemble mean change is relatively insensitive to which specific CMIP6 models you include. So if you do that, you get the following figure, again for the two emission scenarios. And the more red the circles in those figures, the larger the ensemble you need for qualitatively robust projections. There are also circles here with a black edge around them, which indicate that 6 or fewer climate model simulations is sufficient for a consistent sign of the change. And as you can see, especially for the medium emission scenario, this is not the case at very many tide gauges. So that means that previous studies, which were based on only 5 to 6 climate model simulations, are probably qualitatively not robust at these locations. And for a higher emission scenario, this is also still the case for instance, the Bay of Biscay in southwestern France and the northern Mediterranean region. So to summarize, with our new projections of the joint probability of storm surge and precipitation extremes, we found that joint probability will increase in the northwest of Europe and decrease in the most of southwest of Europe. The spatial pattern is quite similar between emission scenarios as well. The changes are driven by a combination of univariate changes in the extremes, as well as changes in the dependent structure between them. And it's very important to emphasize that these projections are very sensitive to internal climate variability. So as I've shown, this can lead to qualitatively different projections, and probably this is the reason why previous studies have obtained qualitatively different results. And for this kind of study that we did, it's also important that new CMIP generations will provide more initial condition members so we can average out that internal climate variability better and provide output at a higher temporal resolution. So we use daily data in this study because that's available for the most CMIP6 models. However, of course, it would have been more ideal to use 6, 3, or even hourly data for this study. Then a few more words. I think personally that applying data-driven models to climate model data, as we did in the study, has quite a large potential because it allows you to kind of circumvent those computational costs of more expensive models. We focused here, as I explained before, on the timing of the storm surge extremes because that's important for computing the joint probability of those extremes with precipitation extremes. But in follow-up research, I'm concentrating more on predicting the magnitude of extreme storm surge as well. And for this, we are using machine learning models based on neural networks. And you see an example of that in this figure below. So again, I'm showing those non-tidal residuals for a location at the Dutch coast in this case. In blue, you can see the observed extremes during the test period. And in orange, you can see predictions made with a convolutional long short-term memory neural network. And as you can see, we get pretty close to those observations. And that means that at least for this location, neural networks could be a viable alternative to hydrodynamic models. And we will investigate how well it works when you apply this kind of model to climate model simulations as well. With that, I would like to thank you, and I'm happy to answer questions, of course.
Great, thank you so much, Tim. That was an excellent presentation. Have we got any questions for Tim? again, either pop your hand up or put it in the chat. Eleanor?
Hi, Tim. Thanks very much for this. This is a bit of a more downstream question, potentially. So if you were trying to explain these results to a policymaker or a decision maker, perhaps who is, responsible for coastal management, how would you sort of describe the uncertainties and how they should utilize the results? Sorry, that's quite a complex question to ask you.
Yeah, but it's an important one, I guess. I think one thing that we still need to work on is to translate the changes that I presented to changes in impact. So I've been talking about changes in joint probability, and to define the extremes, I've set a certain threshold to define extremes above. But I guess what one could also do is to define those extremes based on what you know to be impactful at a certain location. So how much precipitation or how large of a storm surge causes impact at a given location. And I think if we could make that translation step, it would be easier to explain to policymakers how they should take this kind of projection into account.
Great, thank you very much.
Thank you, Eleanor. Zeb's got a question.
Yeah, thanks for the presentation, Tim. Super nice. I was wondering if you could give us a few more reflections on your experience of working with data in the cloud. Like a couple of specifics, like did you have to pay for the compute time, or did Google just give it to you for free as a trial or whatever? And then did you have to get the data in the cloud, or was everything you needed already there? Because that's been an experience we've had, like we use some niche stuff, so it's not already in the Pangeo cloud, and what your thoughts are for how this might look in CMIP 7 as well.
Yeah, so I'm really an end user here. I'm not really maintaining on the maintenance side of things, but I've been working together with Julius Busek from Columbia University. He could probably answer a lot of technical questions. I don't know the extent to which things are paid or not, but I can tell you about the experience of as an end user. So I needed quite specific data with a daily resolution for multiple variables. And indeed, at the start, not all of that data was available. So I've been working with Julius on ingesting the data that was missing. And I think this has taken quite some time. And that ingestion was also still in the development phase at the start. But I think there are sort of structured ways now to request data to be ingested in the cloud. And I think that's starting to work quite well.
Cool, thank you. I don't see any other hands up for now, but again, if you have any more through the rest of the seminar, just put them in the chat and Tim can hopefully answer them for you there. So thanks again, Tim, for that excellent presentation.
Thank you.